Okay, let's talk about circular motion and centripetal acceleration. So what I have here is a rubber stopper on the end of the string. I'm going to spin this around in a vertical circle at a constant speed. The rubber stopper is accelerating. Even though it's moving at a constant speed, it's still accelerating. Remember, acceleration is change in velocity. Velocity is speed plus direction. This rubber stopper is accelerating not because it's changing speed, but because it's changing direction. It's constantly changing direction as it moves in a circle. Now, at any given point of this circle, the rubber stopper has what's called a linear velocity. That linear velocity is tangent to the circle. We can think of the circle as an infinite number of infinitesimally small line segments. Each of those line segments would be tangent to the circle, meaning they're perpendicular to the radius. So what I did here is I drew V1 at this point at the top of the circle, and then a very short time later I drew V2. Now, the magnitude of V1 and V2 are the same because the rubber stopper is moving at a constant speed, but the direction is different. Now what I want to do here is I want to find the change in velocity. So because V1 and V2 are a very infinitesimally small amount of time apart, I'm going to use dV. So I'm going to do V2 minus V1 to get dV. Now, I'm going to do this vectorially. So what I'm going to do is I'm going to take V1, I'm going to flip it 180 degrees to make it negative V1, and I'm going to add it tip to tail to V2. And then this little piece here, so my new vector dV, I draw from the tail of the first vector to the tip of the second. All right, now, because V1 and V2, that's negative V1, are a very short time apart, this is, let's call it d theta. All right, that angle is infinitesimally small. Now, if we know anything about triangles, specifically isosceles triangles, we know that this base, dV, is going to equal the magnitude of these two sides times the angle. All right, now, V2 and V1 have the same size. I'm just going to call it V. All right, so dV is going to equal the side of the isosceles triangle, V, times the angle, d theta. All right, now, if I have something moving in a circle, this arc length, ds, and let's say this is d theta, and I have a radius of r, ds equals r d theta, which means that d theta is ds over r. All right, so I'm going to use that over here. So I'm going to say that dv equals v times ds over r. All right, I'm going to rewrite this. dv equals v over r times ds. All right, now I'm going to divide both sides by dt. All right, since v1 and v2 happen in infinitesimally small amount of time apart, I'm going to divide both sides by dt. Now, we know that dv over dt is acceleration, and if s is the arc length, all right, the change in arc length over the change in time is going to be v. So what we get here is a equals v squared over r. Now, the direction of that acceleration is toward the center of the circle. We know that because dv, the change in velocity, is toward the center of the circle. The acceleration is going to be in the same direction. All right, so whenever something moves in a circle or any curved path, there's always an acceleration toward the center, even if it's moving at a constant speed. This acceleration is called centripetal acceleration. Centripetal literally means center seeking. It's also referred to as radial acceleration because it's along one of the radii of the circle.